Cam 30. We're going to take a crack here at solubility equilibrium, topic number 3, and this is where we see a lot more math being reintroduced. So the solubility product constant is how much of a compound will dissolve in water at 25 degrees Celsius, and it's a constant. So meaning if we have 1 liter of water, we know at 25 degrees Celsius, we know exactly how much will dissolve in it. Substances with no KSP are very soluble, and we have a KSP chart in our reference booklet. It's kind of close to the end there, but you'll see it. It says table D3 solubility product constants for compounds at 25 degrees Celsius. And the very first one that we see there is barium carbonate, this guy here, and it has 5.0 times 10 to the negative 9. Okay, something like sodium chloride isn't on there. We should recognize that sodium, a group 1 metal, is always soluble in water, so its KSP isn't listed. This is only for substances that are low solubility. And we can say the smaller the KSP, the less soluble it is. And generally, when we're looking at the KSP, we're really only looking at the magnitude. We might see something 5 times 10 to the negative 9, as we just saw, or 3 times 10 to the negative 21. This is much smaller, so much less of this substance will dissolve in water than this one here. We can tell just by the exponents. So what is more soluble? I'm going to take a crack at the first two, and then you guys can pause or just sort of try the next two and check your answers. So what I'm going to do here is I'm going to write the KSP values for these two over top of them. So lead to chromate, and it's alphabetized, so you can find them quite quickly. So this is 2.8 times 10 to the negative 13. Or lead to chloride, which is 1.8 times 10 to the negative 8, I think. Chloride, 1.7 times 10 to the negative 5. There it is. So we can see that obviously this one is much smaller, right? We're looking at the exponents here. The smaller the exponent, or the more negative it is, then the least or the lower amount dissolves. So which one is more soluble? PbCl2. There we go. Struggling a bit. Okay, so barium sulfate is 1.1 times 10 to the negative 10. And silver sulfate here is 1.5 times 10 to the negative 5, 1.5 times 10 to the negative 5. So Ag2SO4 is much more soluble. Cobalt hydroxide, 1.3 times 10 to the negative 15. Or copper to carbonate, pardon. And that is, well, there we go, 1.0 times 10 to the negative 10, 1.0 times 10 to the negative 10. So you can see that cobalt, that's supposed to be negative 15. Copper carbonate is more soluble. This one actually looks like cotton candy. I generally make it in my physical science 20 class. It looks really good to eat. Obviously we can't, but copper 2 hydroxide. Where are you? Here we are. 4.8 times 10 to the negative 20. So very insoluble, very small number here. And then sodium chloride. Again, that was the example I just went through. If it's not listed on the KSP chart, it's because it's soluble, or it's a really rare substance. But when you're asked to do this sort of thing, comparing between one and the next, I'll always give you substances that are on the solubility product constant table that's provided in your reference booklet, or you should know that it's a soluble substance. So in the end, NaCl is more soluble than copper 2 hydroxide. Okay, so what we're going to do here is to determine the solubility product constant, we're using these equations here, a dissociation equation. It means if you were to disassociate yourself from someone, it means to break apart or to remove yourself from that influence. So we're going to take our solid here, and you can see AABB, and what that means is some substances, NaCl, we know it's a 1-to-1 ratio. So this would form Na plus and Cl minus. In other substances, let's say we got, for example, copper 1 phosphate, so we'd have Cu3PO4. This breaks up into 3Cu. So this so the subscript becomes the coefficient, and that's what we're seeing here. The subscript becomes that coefficient. And when we write our solubility product constant, normally we do products over reactants, but we can see that this is a solid, so it doesn't appear there, right? So it's just over 1. So we're taking A to the power of A, B to the power of B here, and getting our KSP. So the higher the concentration of these ions, right? So the more that breaks down into these two things, the higher these values are going to be. And in turn, the higher that number is going to be. So if we take, for example, 1 times 4, we get 4. But if we take 0.1 and 0.4, we get 0.04, right? So the smaller these numbers, in the end, the smaller the KSP gets. There's also this. So what we're going to notice is there's more than one way to measure solubility. We can measure a KSP just using that solubility constant that we just saw. Uh, we get that from the molar concentration of ions, right? So the concentration of A multiplied by the concentration of B. So if we know that, we can move into KSP. We can also figure out how much of those ions, right? So if we have something like 3 or 0.03 molar, really what that means is 0.3 moles per liter of water, right? So those are the same sort of terms. They mean the same thing. So if we know moles, if we know that 0.3 moles dissolve in 1 liter, we could figure out how many grams that would be, right? So moles times the grams over the moles, right? Moles would cross out and I'm left with grams. What is this? Grams over moles, we should recognize as being molar mass. And if this is coming at you pretty quick, don't worry about it too much. I'm going to go through lots of examples today. So the very first one here that we're going to do is we're going to determine the solubility product constant for silver bromide. And this is the expression, this is part of the question that we actually really need to know. So the solubility product constant, if we sort of just take the first two letters of this, we get SP, and constant, although it starts with C in our language. Again, most things were discovered in German, or German was important for a long time, so we get KSP. So it's asking us to determine the KSP for silver bromide. And what I would do is I would just get in the habit of writing that out, sort of giving yourself a translation, because you're going to lose a lot of marks if you're trying to solve for the wrong thing. And we'll see that later on. So what we're going to do here is write an expression. So silver bromide, we should know, is AgBr. So we're starting with that solid is at equilibrium with Ag plus aqueous and Br minus. And you're probably thinking, hey, that's an insoluble compound. Why am I writing this as ions? Because we know, or should know at this point, that insoluble compounds will still somewhat dissolve, just barely, but they still somewhat dissolve, and they create that equilibrium, right, of ions, or sorry, solids breaking into ions, ions reforming into solids, and then more breaking down, more going back and forth, right? So that's what that dynamic equilibrium is all about. So if we're doing this, it says the molar solubility is 7.3 times 10 to the negative 7. And although this is a solid, what I'm going to do is I'm going to write that number below here. 7.3 times 10 to the negative 7 molarity. This is saying, this number here, the molar solubility, is telling me how much of this actually will dissolve. So 7.3 times 10 to the negative 7 molarity, so I could sort of imagine that as moles per liter, will dissolve of that substance. So it's not a concentration. I really don't have a concentration of a solid, but I know that much solid will dissolve. So I like to think of it this way. If I've got one car and it's got 4 wheels, if I was to take apart that car, I'd have one body and I'd have 4 wheels, right? And I could get those parts. So if I'm sort of thinking about this one, when I take apart this car, how many silver ions do I get? Well, I get the same number. So if 7.3 times 10 to the negative 7 moles, or moles per liter of silver bromide breaks down, I would have 7.3 times 10 to the negative 7 molarity of that ion. It's a 1-to-1 ratio. So if 1 mole of this would break down, I'd get 1 mole of that. And if 2 moles of this would break down, I get 2 moles of that. And I can see the same thing for the bromide too. So this is going to be 7.3 times 10 to the negative 7 as well, right? The coefficient here of a 1 and a 1 and a 1 means that I'm going to have equal sort of concentrations across the board. Now, it's telling me to calculate the KSP. So I'm going to write the KSP expression for this. So it is going to be the concentration of silver, and I'm using square brackets here, multiplied by the concentration of bromine. So the concentration of silver is 7.3 times 10 to the negative 7 at equilibrium, and 7.3 times 10 to the negative 7. So when I do the math here, this works out to being 5.3 times 10 to the negative 13. And we should notice something here real quick. When we multiply two terms, You might have recognized this from your pre-cal days. If we have a times m, sorry, let's try that again. A times 10 to the m multiplied by b times 10 to the n. What this works out to being is a times b times 10 to m plus n. So really, if we want to do this, we could do this as 7.3 times 7.3 times 10 to the power of -7 plus -7. So we know you might be looking at this and going, well, 5.3, -7 plus -7 is not -13. You're right. But when we multiply 7 times 7, we get something close to 49 times 10 to the -14. And scientific notation is always one decimal place. So we'd move that decimal over one to the left, which would cause that to get one bigger. So I guess what I'm saying is you're never going to have to do this sort of math on your own. You got a calculator for that. But what you should be able to do is check to see if your answer is right. So I know that -7 plus -7 is -14. So I'd expect my answer to be within one or two of that. So either -13 or -15, one of those two numbers. What often happens here is students, because they see two of them, they'll just take 7.3 times 10 to the -7 and multiply by 2. And you're going to get something like 1.41 times 10 to the -8 or times 10 to the -6. And that should be a bit of an alarm, right? -6 is nowhere close to -14. Like, I must have done something wrong. So go back and recalculate it. Okay, so that's calculating the molar solubility, or sorry, the solubility product constant when given the molar solubility. So for the main part of this, we're either going to be going KSP to the concentration, how much will dissolve of a solid, or the concentration to KSP, right? Those are the two things that we're really going to be doing for the most part. Okay, example number 2 here, we're going to determine the solubility product constant of magnesium 2-phosphate if the solubility is measured to be 9.8 times 10 to the -7 molarity. So again, we're moving from the solubility, the molar solubility to KSP, right? So we're calculating this again. We're just going to see something a little bit different with this one because we don't have ions are in a 1-to-1 proportion. So manganese 2-phosphate, Mn2 plus, manganese, not magnesium. Be careful with that. Phosphate, PO4, 3 minus. So we should get Mn3 bracket PO4, 2, solid, decomposes into 3Mn2 plus, aqueous, and 2PO4, 3 minus, aqueous. Okay, so anytime I'm working with a molar solubility, it goes right here. This is where we're going to always stick the molar solubility if we are given that number. So in this case here, it is 9.8 times 10 to the -7. So in this case here, we know that the concentration of manganese 2-phosphate that dissolves is 9.8 times 10 to the -7. But it's not going to be the same numbers for the manganese ion and the phosphate ion. Why? Because in this case, when this one car breaks down, it provides 3 of these ions and 2 of these ions. So if that's the case, what is the concentration of the Mn2 plus going to be? Well, it's going to be 3 times 9.8 times 10 to the -7. Right? For every one of these that break down, I get 3 of these. It's just multiplied by the coefficient. And in this case here, it's going to be 2 times that same number, 9.8 times 10 to the -7. So what I like to do when I'm doing these is calculate it in 2 steps. So I'm going to figure out 3 brackets using my calculator, using brackets when I'm calculating. It's important when we're getting into scientific notation, your calculator will try and do things out of order occasionally. So you should be following along and doing these same calculations as me. So this works out to being 2.94 times 10 to the -6. Fix that, there we go, times 10 to the -6. And this works out to being, I'm going to just divide that answer, multiply by 2 instead, 1.96 times 10 to the -6 here. Okay, so those are my concentrations for those two things. I'm going to set up my KSP equation just as I did before. So KSP is equal to the concentration of Mn2 plus and the concentration of, I need a little bit more room here, PO4 3 minus. Notice I'm writing the charges inside the brackets, right? The charges still exist. I'm taking the concentration of those ions, and those ions are represented by charges, so it should appear in the KSP expression. I've purposely made a mistake here. Hopefully you recognize that this should be a 3 here and a 2 here. So if you're sort of keeping track, I multiplied by 3 here, and then I'm cubing it down there. So there's this big effect, okay? It's not just multiplying by 3. I'm multiplying it by 3, then cubing it. When we go from here to here, this is sort of the concentration is multiplied by 3 because of something called reaction kinetics. Just the number of particles, the kinetics involved with that is different. So then when we cube it here, this is different. This is a function of equilibrium. We don't have to understand it at our level of chemistry. We just need to make sure that we're doing it correctly. So we're going to multiply by 3 and cube it. So this works out to being 2.94 times 10 to the negative 6 cubed multiplied by 1.96 times 10 to the negative 6 squared. So when we have exponents, if we had a to the power of m and then n outside the brackets, it's the equivalent of a m times n. So if we had 2 to the power of 3 and this was 4 outside, we would expect this to be the same as 2 to the power of 12. Because really what we're doing here is going 2 to the 3, 2 to the 3, 2 to the 3, and there we go, 2 to the 3, 4 times. So those are equivalent. And as we do that, we should know that when we multiply, we're really just adding the exponent. So in the end, this works out to being 9.76 times 10 to the negative 29. So before I walk away from this question, I should again sort of, does this seem reasonable? So my first term here, negative 6 times 3 is negative 18, multiplied by, this is negative 12. So when I add those two together, I get negative 30. Is that close? Yes. Okay, so in this class, it's always going to be a good enough check to be doing that. If you get reasonably close for the most part, you're going to have the right answer. A question like this is generally out of 3 or 4. And if you got, if you showed all this work, you would easily get, if this question was out of 4, I'd be giving you 3.5. Assuming that, sometimes there's a calculator error and you lose a mark there, but you're losing only 12.5%. So not a big portion. If you give me no information or you do something wrong, or for example, if you just write manganese phosphate is MnPO4 and you break this in Mn3 plus and PO4 3 minus, and you get real lazy like that, this is going to be X, or this is going to be just multiplied by 1 or not multiplied at all. So you're going to get a number that's way off, right? So you're looking at, if you're doing that sort of mistake and you're even showing all your work, you're getting a 2 out of 4, right? So it's critically important to make sure that you're getting your formulas right. Otherwise, you're going to be hooped right from the beginning of the question. Okay, example number 3 here. We're going to determine the solubility of silver bromide in moles per liter at 25 degrees Celsius. So we're giving no information here. The temperature for us is a useless thing because all KSPs are calculated based on the water being 25 degrees Celsius. We should recognize that as the water temperature increases, the solubility increases, right? So we're having that standard of 25 degrees Celsius, but it offers no information for us. So what are we going to do? We're going to calculate the solubility based on the KSP that is provided to us in the table in our reference book. So when I look up the KSP for silver bromide, AgBr, I find it to be 5.0 times 10 to the negative 13. Okay, so I'm going to write out the equation here. AgBr solid is at equilibrium with Ag plus aqueous and Br minus aqueous. And at this point, we don't know the molar solubility. That would be equal to X. We don't know how much that is, right? We're always placing the molar solubility over here. So I'm just going to write a little MS right here. That's the molar solubility. But let's imagine this. If the molar solubility of AgBr solid was X, what would the molar or the concentration of this silver ion be? Well, it would also be X. It's a 1-to-1 ratio. And if that's X, what is this? Well, that's also X. It's the same number, right? So for every 1 mole of these that dissolves, I get 1 mole of these ions and 1 mole of these ions. We can see that with the balanced chemical reaction, 1, 1, and 1. So I'm going to take that information and write into a KSP equation. So KSP is equal to the concentration of silver multiplied by the concentration of bromine. In this case, the KSP is equal to 5.0 times 10 to the negative 13. We have that piece of information. What's the concentration of silver at this point? Well, it's X. What's the concentration of bromine? Also X. So we get 5.0 times 10 to the negative 13 is equal to X squared. How do we get rid of that square? We don't want to know X squared. We want to know the concentration of X. So we are going to square root this. So we square root this and we square root this, and we get X is equal to 7.07 times 10 to the negative 7. Now, if you were to give me this answer, I'd give you a solid 2.5 out of 3. Why? Because all you've told me is what X equals. But X could mean this. Do I really want to know the concentration of bromine when it's fully saturated? No. Or do I want to know the concentration of silver? No, I want to know this. So the way I'm expecting your answers to be is the molar solubility. So we're going to write this in square brackets. The molar solubility of AgBr is equal to 7.07 times 10 to the negative 7. Basically, what's happening here is we've got our beaker and we've got some solid. So we know that this solid, for the most part, is insoluble. But insoluble, really nothing's 100% insoluble. So there's a very little concentration. So if we were to actually measure the concentration of the liquid here, we would find out that 7.07 to the negative 7.07 times 10 to the negative 7 moles per liter of that solid actually dissolved. That's what we're calculating here. So these X's represent the concentration of those ions at equilibrium. And overall, we can calculate the molar solubility based on those ions. Okay. Example number 3 or 4, I don't know, one of the two. We are going to determine the concentration of fluoride ions in a saturated solution of magnesium fluoride if the KSP is 5.6 times 10 to the negative 11. So nothing too difficult here. We just need to make sure that we get the ions right. So magnesium 2 plus pardon, and fluorine minus. So we get MgF2 solid is at equilibrium with A or Mg2 plus and 2F minus aqueous. Okay, so this one here, we are going from KSP to the concentration of fluoride ions in a saturated solution. So what we're going to try and do here is here's our solution. We've thrown a whole bunch of magnesium fluoride in, just lots. We're going to use a real technical term. How much do we have here? Lots. How much dissolves? Some. Question mark. We don't know. We don't have a molar solubility. But if we did have a molar solubility, right, if we know that 5 moles dissolve in 1 liter, in this case, if 5 moles, if this was 5 big M, then this would be 10 big M. So if we can figure out this number here, we can figure out how much fluorine will have dissolved, right? So that's what we're searching to do here based on a KSP. So we don't have this molar solubility number, right? We're given a KSP. This is the box for molar solubility. So we're going to have to do that same sort of thing. So we're going to assume this is X. And if this is X, this is X here. And this, be careful, is 2X. For every 1 mole of this substance, I get 2 moles of these ions. So when I'm doing this, KSP is equal to concentration of Mg2 plus F minus squared. So this works out to being 5.6 times 10 to the negative 11 is equal to X times 2X squared. And guarantee at least one of you will make this mistake. 2X squared is 4X squared. No, some of you will just make this, call it 2X. No, that's not right. That's what I'm doing wrong. So 2X squared is equal to 4X. Or I'll get this, I will get lots of 2X to the 4. No, 2X squared is the same as 2X times 2X, which is 4X squared. So be really careful about that. So we get 5.6 times 10 to the negative 11 is equal to 4X to the power of 3. right? So x times this works out to being 4x3. So what do I have to do? Order of operation matters. What do we want to do? We want to get rid of this 4 first. So what are we going to do? Divide by 4. So be careful with that. Don't be lazy. Really pay attention to what you're doing. So we're going to divide by 4. We're going to divide by 4. So we got 5.6 times 10 to the negative 11 equals divide by 4 equals. So my calculator displays this as 1.4 times 10 to the negative 11 is equal to x to the power of 3. How do I get rid of 3? I cube root this now. So I cube root this. Make sure you know how to do that in your calculator. For the most part, you'll have a button on your calculator that looks like this, where we've got a little box, and then we have a square root sign, and then another little box. You generally will put the number 3. Hit this button, and then put in your answer there, and it'll do it for you. So this works out on my calculator. I can do it all in one step. If you can operate your calculator like that, I advise you to do so. So mine, oh no, I screwed up. Oh well. Cube root of 1.4 times 10 to the negative 11 equals to 2.41. 2.41 times 10 to the negative 4 is what x is equal to. And you're thinking, well, this guy's a dum-dum, because how can that possibly be the answer when that's the answer down there in the right corner? Well, we have to be careful. We've solved for x. In this case, the question's asking us for the concentration of the fluoride ions. Where are the fluoride ions? Oh, that's a bad choice of color there. Let's go with this one. There we go. Okay, so the fluoride ions are represented by 2x. So what am I going to do? I'm going to take the concentration of x and multiply it by 2. So 2 times 2.41 times 10 to the negative 4 is equal to 4.82 times 10 to the negative 4. Okay, so keep in mind that when you multiply by 2, the multiplying by a number here, right, any number, is really only affecting the base of this term, not the exponent. Okay, so when we're doing this, we're really only affecting the base. So 2 times 2 is 4, 0.41 times 2 is 0.82, so we get 4.82. And I would mark you still wrong on this one. 3 out of 4. The answer I'm looking for is the concentration of F minus is equal to 4.82 times 10 to the negative 4 big M. I'm looking for concentration is always measured in M. If you wrote this as moles per liter, same thing. I'd give you the mark on that one. Okay, last example here. What mass of chromium-3 hydroxide is able to dissolve in 500 milliliters of water if the KSP of chromium-3 hydroxide is 1.6 times 10 to the negative 30? This is one of those bigger questions. I generally don't stick it on quizzes or exams, but depending on how well we're doing with this, you might see it somewhere. So you'll notice the big difference here is we're asking how much mass dissolves in 500 milliliters of water. So what we're really going to try and do here is, if we figure out the moles per liter of chromium, we can convert moles to grams by using the molar mass. There we go, molar mass, which is from the periodic table. I know it's been a long time since you've done that. I know Physical Science 20 was a bit ago, but you'll be able to sort of knock some rust off there and do it real quick. And then in 1 liter. So basically this is saying, if we figure out the moles per liter, it's the amount of moles that will dissolve in 1 liter. So if we're asking ourselves 500 milliliters, what we can do is just a little bit of dimensional analysis, right? So if we have something over 1 liter and we multiply in 1 liter, there's 500 milliliters. Oh, that's not true. We're just going to multiply by 0.500 liters. So the liters are going to cross out, and then we're going to be left with grams on the top, right? So we're going to have grams up here. I know this doesn't really make sense from where we're sitting right now, but it will in just a couple of minutes. So we are given a KSP. So we're going to work back from KSP to molar solubility, right? So moles per liter, and then we're going to work on the top, and we're going to use molar mass. And then we're going to work on the bottom by multiplying by 0.500. So first thing that we need to do here is set up our equation. So Cr bracket OH 3 solid is at equilibrium with chromium 3 aqueous and 3 hydroxide ions. So we don't know the molar solubility, so we're going to represent that as X. If that's X, we should know that the concentration of chromium is also X, and this is going to be 3X. So when we write our KSP expression, we get KSP is equal to bracket Cr3 plus multiplied by OH minus cubed. So we get 1.6 times 10 to the negative 30 is equal to X times 3X cubed. Guarantee again, one person always does this, 3x cubed. Okay, that's 9x. And then they just go through the operation here. So they go, oh, this is equal to 9x squared. Nope, you're wrong. Okay. I will mark you wrong with a vengeance because it irritates me, honestly, at this point, because it's just not paying attention. It's not focusing on what we're doing here. So if we imagine this 3x times 3x times 3x, right? That's really what we're doing. 3 times 3 is 9, times 3 is 27. X times x times x, x to the 3. So what are we going to get here? We're going to get x to the 3 multiplied by this. So we're going to have 1.6 times 10 to the negative 30 is equal to 27x to the 4. So what's the first step? Well, we're going to divide by 27. Divide by 27. And then, and I'm just going to show this all in one step because I run out of room on this question all the time. So I'm going to root it to the 4th power. Now, if you want to work around, just so you're aware, if your calculator doesn't have a fancy button for this and you can put fractions or you can sort of cheat the system, you can go any number. So let's say 8, for example. If you were to cube root 8, that's equal to 2. If you go 8 to the power of 1 divided by 3, right? You can put in those buttons so that we have, on most calculators, you'd go something like 8, exponent button, and then bracket 1 divided by 3. It will work out to being 2. Okay, so in this case here, if you divide it by 27 and you got some number, you could take whatever that number is and put it to the power of 1 divided by 4. That's the same as having the 4th root. Okay, so I will not show you how to use your calculator on a quiz. You need to know how to use it before then. It's really important that you're sort of proficient with it. So we're going 1.6 times 10 to the negative 30 equals, so I get it in there as a term, then I divide by 27 equals, then I'm going to use my fancy button where I'm going to take it to the 4th root, and I get 1.56 times 10 to the negative 8. And just so we're aware, when we root things, let's say we have x to the 40 and we're taking it to the 4th root, that's equal to x to the 10. So basically we're dividing, right? So just as a check, people do this wrong. You punch it into the calculator, or your calculator, you didn't use brackets correctly, so then it does order of operations sort of funky on you. Just be aware of that. So when we're taking the 4th root, I'd expect 30 over 4 is somewhere around 8, 7 or 8. That's where my answer is going to be, just as a check. Okay, so what this means is this number, I'm going to go, let's go with black. So 1.56 times 10 to the negative 8 moles of chromium hydroxide will dissolve in 1 liter of water. That's what this number means so far. So what do I want to do here is I want to transform either the top or the bottom. So I'm going to work on the top first. I'm going to get that into grams because that's what's asking us here, right? The mass. Mass is measured in grams. So I'm going to get rid of moles. So 1 mole of Cr bracket OH3 is equal to the molar mass. So when I'm calculating that under the squiggly line here, I'm going to take chromium multiplied by 1, oxygen and multiply by 3, and hydrogen multiplied by 3 as well. So I get, let's do this real quick. So chromium is 52 flat, so 52.00 plus bracket 3 times 16, bracket plus 3 times 1.01 equals bracket, or we get 103.03 grams per mole. Oh boy. There we go. So 103.03 grams per mole. Now, depending on who taught you PS20, you should recognize what I'm about to do here. Moles and moles cross off, right? Those are units. Um, equivalent units, they get rid of them. And the way this works, this is what we call a conversion factor, this little section here. This conversion factor, the only way that conversion factors work is if the top and the bottom are equivalent. So the way I like to imagine this, if I had 103 grams of this substance here, it would be 1 mole. Or in another beaker, if I placed 1 mole of it, let's say I was able to magically measure that, it would have the exact same size and weight as 103.03 grams. So these things really mean the same thing. In the same way that 1 day is equal to 24 hours. So if I had 2 days and I wanted to convert this to hour, 2 days multiplied by 24 hours in 1 day, days cross off, right? 2 times 24 is 48. So is there 48 hours in 1 day? Well, there sure as heck are. So this works out, right? This math sort of makes sense. So that's left. Now I want to get rid of this liter on the bottom. So and it's asking me how much dissolves in 500 milliliters. So what I'm going to do is I'm going to convert that to liters, right? So 500 milliliters divided by 1,000. When we're going from liters to milliliters, we're dividing by 1,000. Okay, so this works out to 0.500 liters. So I multiply by that, 0.500 liters. So liters are now, I guess I should use red here. Liters are going to cross out. So what unit am I left with? I'm left with just grams. Let's go with purple. This is sort of a mess. Like I said, running out of room. So the only unit I'm left with here is this little grams. So when I do this, I'm multiplying everything on the top and divide by everything on the bottom. So you'll notice that there's nothing on the bottom. Okay, so I'm going to take bracket 1.56 times 10 to the negative 8 bracket times 103.03 bracket 0.5 bracket equals, and I get 8.03 times 10 to the negative 7. Nope, 8.036. So 8.04 times 10 to the negative 7 grams. And that seems like a ridiculously small amount. So we've got 8.04 times 10 to the negative 7 grams. So that is 0.00000000804 grams. So we're at tenths, 100,000, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths. So it will dissolve 800 millionths of a gram. Does that seem like a lot? No, of course not, because we're working with an insoluble compound, right? That's the whole idea of this. So basically, in 500 milliliters, 8/100 millionths of a gram will dissolve. And that's what we'd expect. If we get a big number there, obviously we've done goofed somewhere. Okay, this is the last example. This is a really complicated one. There's a couple of the practice questions that you can do with these ones in it. I advise you to certainly stretch and certainly try these ones because they're going to pop up. If you have a good understanding of how to work with this one, the next topic that we're going to do is going to work out really well for you. Okay, so put in the extra time and practice on this topic so you can really understand and get number 4 without having a bunch of issues. Okay, that's it. Hopefully this this made sense. And if you have questions, fire off an email or somehow contact me so you can ask and we can schedule something.